Okay, here's sample problem 15.9. For the same reaction in temperature as in sample problem 15.8, calculate the equilibrium concentrations of all three species if the starting concentrations are as follows. The concentration of H2 is 0.00623 molar. The concentration of I2 is 0.00414 molar. And the concentration of HI is 0.0424 molar. Okay, so let's write the equation out here. It's the same reaction as we saw in the previous example. Hydrogen plus iodine to form HI. And the equilibrium constant should be the same, 54.3. Okay, I'm going to write out our initial concentrations here. The initial concentration of H2 is 0.00623. I'll leave the units out just to save a little space here. I2 is 0.00414. And HI is 0.0424. Okay, so we need to figure out whether we're at equilibrium, so we calculate Q sub C. So that would be the concentration of HI squared, so that would be 0.0424 squared, divided by the concentration of H2, which is 0.00623, divided by the concentration of I2, which is 0.00414. Yeah, if you plug those in, what you get is 69.7 is what I get. Okay, so that tells us that Q is greater than K, which means the reaction is going to go toward the reactant side. So you'll have minus 2x on the left, and then plus x for all of the reactants. Okay, so plus x for H2, plus x for I2, and then minus 2x for HI. And then at equilibrium, we just add the two terms together, add the top and the middle. So that would be 0.00623 plus x, 0.00414 plus x, and then 0.0424 minus 2x. Okay? So now we do have the value of K, and now we have an expression. So let's take a look. K C is 54.3, and that would be equal to the concentration of HI squared. So that would be 0.0424 minus 2x squared. And then we're going to divide that by 0.00623 minus x, and 0.00414. I'm sorry, that's plus x. Plus x. Be very careful with these calculations, particularly the earlier you make a mistake in these problems, the more problematic it becomes. So with the previous example, 15.8, we were able to take the square root of both sides because the numerator was a term squared, and the denominator was a term squared. But that's not the case here. The denominator has two different terms. 0.00623 is different from 0.00414. So we cannot take the square root of both sides. So we have to do this the long way, or one way to do this is the long way. We have to expand everything out and solve for x using the quadratic formula. Okay, so the strategy here will be to use algebra to solve for x, figure out what x is, and then plug them back into our equilibrium concentrations to find the equilibrium values for all of the reactants and products. So the first step, or a first step, would be to expand the numerator. Take 0.0424 minus 2x and then square that. And so the way you do that is you take the first term, which is 0.0424, and you square it. And that gives you, I'm going to put over here, I'll put the 54.3 on the right and then make a lot of space over here on the left. So 0.0424 squared is 1.806 times 10 to the minus 3. Then we multiply this 2x by 0.0424 and then double it. Okay, so 0.0424 squared minus 2 times 0.0424 times minus 2x. So you get minus 0.1696x. If you're having a problem with that step, I'll just write over down here that if you have a plus or minus b squared, you square the first term, so a squared, and then it's plus or minus 2 times a times b. So you multiply the a and the b together, and then you double it, and then plus b squared. The reason it's plus b squared is that even if b is negative, negative b squared, quantity negative b squared, would be plus b squared. Okay, so that's what we're doing at the top. So when you double the 2 and the 0.0424, you get 0.1696. Okay, and then we're going to square the second term, so that's plus 4x squared. Then in the denominator, I'm going to put a little room here. In the denominator, we're just going to take the 0.00623 and multiply it by both terms in the second parentheses, 0.00414 and then x, and then take the second term in the first parentheses, which is x, and multiply that by each of the two terms in the second parentheses, 0.00414 and then x. Okay, so that gives you 2.579 times 10 to the minus 5 plus 0.00623x plus 0.00414x plus x squared. Okay, let me make this a little bit longer and then put the equal sign over there, and then get rid of this up here. Okay. Now, if you take a look at the denominator, you will notice that there are two terms that are in x. So those can be combined into one term. So the next step then, I'm just going to copy everything down in the numerator. And then I'm going to combine the two x terms in the denominator. So again, 2.579 times 10 to the minus 5 plus 0.01037 x plus 4x squared. And again, that's equal to 54.3. Okay, so we're getting there. So the next step is, what we're really trying to do is we're trying to get this whole thing into a form that looks something like this, the general form for a quadratic. See there? Ax squared plus bx squared, plus bx plus c. That's the general form for a quadratic. So to do that, the next step I'm going to do is I'm going to take everything that's in the denominator and multiply it by the 54.3, the equilibrium constant. And that will put everything up in the numerator. Okay? So 3 terms times 54.3. So what I'll do here is just copy down the numerator again. You have to be very organized when you do these. And then 54.3 times everything in the denominator. Okay. Then you multiply, you distribute, right? You distribute the 54.3 through all three of those terms. So again, copy this down. I find that I have to just go through this very stepwise. It's hard for me to make any shortcuts on this. So you get 1.400 times 10 to the minus 3 plus 0.5631x plus 50, oops, let me see here. Oh, I'm sorry. I see what I did. I made a mistake here. So if you catch these mistakes, you'll see what happens, right? It was x squared in the denominator, not 4x squared. So x squared in the denominator, so then 54.3 times that would be 54.3x squared. There we go. Okay. So now we have everything in one line. Now what we can do is we can start combining like terms. So I'm going to choose to put everything on the right side of the equation over here so that our leading coefficient is positive. So I'm going to move everything from the left over to the right. So the way we do that is we do the operation that makes it 0 on the left. So if this is plus 4x squared on the left, subtracting 4x squared will make that 0. And if this is negative 0.1696x, adding 0.1696x, we'll get rid of that one. And then if it's positive 1.806 times 10 to the minus 3, subtracting that, we'll make that 0. However, you have to do the same thing on the right side that you do on the left in order to maintain the equality. So we're going to have to subtract 1.806 times 10 to the minus 3. We're going to have to add 0.1696x, and then we're going to have to subtract the 4x squared. Okay, so that'll make it 0 on the left side, right? Because those add up to 0, those add up to 0, and those add up to 0. So we have 0 on the left side. Then we add everything together on the right side. So when we do that, we have negative 4.06 times 10 to the minus 4. We have plus 0.7327x, and then we have plus 50.3x squared. Okay, a lot of work to get to that point. Now, however, we have it in the form of a quadratic. ax squared, so a is 50.3, plus bx, so b is 0.7327, and then plus c is this term right here, negative 4.06 times 10 to the minus 4. So this is c, this is b, and then the 50.3 is the a, not the x squared, it's ax squared. So we have our coefficients. Now we can use the quadratic formula to solve for x. I'm going to go ahead and erase all of this hard work because we need the space, right? So a is minus 4.06 times 10 to the minus 4. B is 0.7327. And c is 50.3. So now, the quadratic formula says that x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Okay? So now we can get rid of this down here. Okay. All right, so let's plug those numbers in. So minus b. So this would be equal to minus 0.7327 plus or minus the square root of b squared. So 0.7327 squared minus 4 times minus 4.06 times 10 to the minus 4. Oops, sorry. I think I have this reversed. This is actually 50.3. And this one is minus 4.06 times 10 to the minus 4. Sorry about that. Okay. So let me just get it in the correct order here. $50.3, and then times minus 4.06 times 10 to the minus 4. 4ac all over 2a. So 2 times 50.3. Okay. All right, so how do we deal with this? Well, one way to deal with this would just be to figure out what the number in the radical is under the square root sign. Notice that when you're subtracting 4ac, c is negative, so you're subtracting 4ac and c is negative. A result of that would be it's like adding 4ac where c is positive. And so when you do that operation, we should end up with 0.6185. Okay, so check, make sure you're careful on that step. And then 2 times 50.3 is 100.6. Okay, so again, this is x. Be careful on that step. Make sure that you get that 0.6185 or something pretty close to it. And this is plus or minus. Okay, so now the next step could be to just go ahead and evaluate that. What is the square root of 0.6185? So this would be minus 0.7327 plus or minus 0.7865. Divided by 100.6. Okay. So now the plus or minus means that you're going to do two separate calculations. You're going to do the positive root. So that would be the minus 0.7327 plus 0.7865 over 100.6. And then you're separately going to do the negative root. So that would be minus 0.7327 minus 0.7865 over 100.6. Let me see if we can't seem to get rid of that. Okay. All right. So running it through, what you end up with are two values. The positive root is 5.348 times 10 to the minus 4. And the negative root is minus 0.0151. So I'm going to box those in because those are important numbers now. We have two different answers. And again, check through all these. Make sure you're getting the same thing. We're now going to evaluate which of those two roots, which of those two results are the ones we want to use, is the one that we want to use. Which one? So again, let's get rid of all this hard work so that we can make space for the next step. Now, let's try both of them. Suppose that we took the first value, x plus, and I'm just going to look at one of the materials. I'm just going to look at H2. So at equilibrium, for the positive root, we would have 0.00623 plus 5.348 times 10 to the minus 4. Okay? Is that a possible answer? Well, let's put them both into scientific notation, but also with the same power of 10, the same exponent. And I'm going to pick negative 4 as the exponent since the second number is already negative 4. So I'm going to put this into negative 4. 1, 2, 3, 4. So this would be 62.3 times 10 to the minus 4. Remember, with scientific notation, you move the decimal point to the right the number of spaces until you get where you want to get. So I moved it 4 spaces so that it would be 10 to the minus 4. Now I can add this, 5.348 times 10 to the minus 4. And if you do this calculation, you get 67.648 times 10 to the minus 4. Okay, seems possible, right? It's a plausible answer. Now let's try the negative root. The negative root says that x is minus 0.0151. So let's try that one. 0.00623 plus a negative 0.0151. And again, let's put them into scientific notation. For this one, I'll go to the third, negative third. So I'll move it 3 spaces for each of them. So 1, 2, 3. So this would be 6.23 times 10 to the minus 3 minus, let's do this 3, 15.1 times 10 to the minus 3. The reason that we want to have the exponents be the same value is so that you can add the decimal numbers directly or subtract that or subtract. Now what stands out about this calculation here? Look at those two numbers. This number minus this one. What would we end up if we did that calculation? You see, if you take a number that's larger and you subtract it from a number that's smaller, you get a negative value. So that would tell us that our result would be negative. We would have a negative concentration of H2 at equilibrium. Is that possible? You can have a negative. Can you have a negative concentration? That's actually a rhetorical question. You cannot have a negative concentration. So that's not a plausible answer. So that negative 0.0151, although it works out through the quadratic formula to be one of the roots, it's not the root that we're looking for. The one we're looking for is the more plausible one, which was the positive root, which was the 5.348 times 10 to the minus 4. So we're going to use the positive root, and we're going to reject the negative root. Okay? So we've already done one of the calculations, but let's go through it formally and do all 3 of the concentrations at equilibrium. Okay. So at equilibrium, the concentration of H2 would be 0.00623 plus X. The concentration of I2 at equilibrium would be 0.00414 plus X, which is 5.348 times 10 to the minus 4. And the concentration of HI at equilibrium would be 0.0424 minus 2X. Okay? Now, if we go through those calculations, the result that you end up with is for the H2, you get 6.76 times 10 to the minus 3. Okay. For the I2, you get 4.67 times 10 to the minus 3. And for the HI, you get 4.13 times 10 to the minus 2. Now, let's check to see whether those answers are reasonable. We've done a lot of work on this problem, so let's see if it's correct. The equilibrium constant is 54.3. So let's see if this works out. We're going to substitute those numbers, 4.13 times 10 to the minus 2 squared, divided by 6.76 times 10 to the minus 3, divided by 4.67 times 10 to the minus 3. Oops, there we go. So 6.76, 4.67, and then in the numerator, 4.13 times 10 to the minus 2. Okay? Well, when I do this, I get 54.0. Now, that's not exactly 54.3, but it's pretty darn close. It'd be hard to get it much closer than that. So the fact that this is approximately equal to 54.3 tells us, yes, we've got pretty much the right answer. Okay? So there we go. The final answer in scientific notation would be right here. And if you wanted to put it into decimal notation, we could do that as well. We would have 0.00676 molar for the H2, 0.00467 molar for the I2, and 0.0413 molar for the HI. Okay, so that's in decimal notation. These three here are in scientific notation. Okay, there you go. That one takes a lot of steps. It's very easy to make mistakes. Just so if you feel bad if you get it wrong the first time, don't feel bad about it. Just want to keep practicing these problems. I would say do this one. If you get it right, that's fine. If you do it right the first time. If you don't get it right the first time, try it again. Start afresh. It's very easy to make mistakes here because the numbers, you may have taken the quadratic formula and done quadratics in algebra, but you will often have very easy coefficients like 2, 3, 5 in an algebra class. Here we have coefficients that are not so simple because our concentrations are 0.00623, 0.00414, 0.0424. These numbers are not so simple, so it makes the algebra a little bit more complicated. Not the algebra, but the actual calculations a little more complicated. Okay? So be organized and then practice.